Let's look at question number 5 from the 2025 AP Calculus BC exam. This was a BC specific question. I have not read the question yet. I have only looked at them closely enough to know what was and was not shared with the AB exam. So you're going to get to see me read this problem for the first time and process it without a polished solution pre-rehearsed. So if I make mistakes, point them out in the comments, which I very well might make a mistake. I usually do at some point in the 9 FRQs that I work out every year. So let's look at this one. So number 5, they give me a differential. Oh, AB didn't have a differential equation problem. I just now realized that. That's frustrating, I guess. So no diffie-q problem for AB. So that's 3 minus x times y squared is my differential equation. I'll go ahead and write down the initial condition as well. F of 1 is negative 1. All right, find f double prime of negative 1 and show the work that leads to your answer. So my second derivative for question A, you just have to remember this is an implicit problem. D squared y over dx squared is going to be the derivative of 3 minus x. That's negative 1 times y squared plus 3 minus x times the derivative of y squared, which is 2y. However, we are differentiating with respect to x. Y is not x, so we give it the implicit treatment, dy dt, dy dx, and it only asks for the value. They very frequently ask you to write the second derivative in terms of x and y. They did not do that, so that's going to open the door for me to do a few to make this a little bit easier on myself. So the second derivative, when my point x, y is, I assume 1, negative 1, yeah. 1, negative 1, and I'm going to plug that in. So it's going to be negative 1 times y, which is negative 1 squared, minus 3 times x, which is 1, times 2 times y, which is negative 1. And then dy dx, I'm just going to evaluate dy dx at 1, negative 1 over here. So that'll be 3 minus 1 times negative 1 squared, which ends up being 2. And I will just import the value of 2 for dy dx there. And that's your answer. That is an acceptable answer. If you want to clean that up like some silly willy, you don't need to, but that would be negative 1 minus 2 times negative 4. Is that negative 1 plus 8? Is that 7? Is it 7? I think it's 7, but let's not risk it. Let's leave it as ugly and numeric as we can. Just make sure it's all numeric when you stop. Number B, oh my gosh. They put 2 series questions on the AP exam this year? I bet they did, because number 6 is always series, right? The second degree Taylor polynomial for f about x equals 1. This is going to be pretty convenient, and this is where that value of 7 is actually going to come in handy. I'm going to use the generic formula, the nth derivative at 1 over n factorial times x minus 1 to the nth, and we're going to do that for n equals 0, 1, and 2. Well, the 0th derivative is f of 1, so that's going to be negative 1 plus f prime would be the value of the derivative at this point, which I found out was 2 over here. So that's going to be 2 over, and I like to put over 1 factorial, although that's not needed, times x minus 1 to the first. And then the value of my second derivative, here's where that 7 is going to come in handy. So I may double check that I did that correctly. So that's negative 1 minus 2 times negative 4. Yeah, I like the 7. I like the answer of 7. 7 over 2 factorial, which is just 7 halves, times x minus 1 to the 2th. And that's it. You're done with B. So that's actually, even though it's a series question, which people tend to get really anxious with series, that one's not bad. The second degree Taylor polynomial is used to approximate f of 1.1. It is known that the third derivative is always less than 60. Here comes Lagrange. And yep, there it is. Use the Lagrange error bound to show that this approximation differs from f of 1.1 by at most 0.1. So Lagrange. All right, so my error for Lagrange is always going to be less than or equal to the, I'm going to write down the generic expression, the max of the absolute value of my next derivative, which I'll write n plus 1 of x all over n plus 1 factorial times x minus c to the n plus 1 power, and that should be in absolute values actually. So there's your generic expression. And then if I plug in my actual values, this would be the maximum of the next derivative they give you is 60 over, and we used the second degree polynomial. Yeah, so that means n is 2, so it'll be 3 factorial. And then it'd be times, and we plugged in 1.1, so it'll be 1.1 is the x value that we plugged in. The center of the series is 1, and we'll raise that to the 2 plus 1 power. And that is 60. And what I like to do on these, they tell you that the error is supposed to be less than 0.01. So my target is 1 over 100. So that's what I'm aiming for. And I want to do enough work just to see that I am actually achieving that. So 3 factorial times 1.1 minus 1 is 1/10 to the 3rd power. 60 over 3 factorial, 60 over 6 is 10. That's going to be 1 over 100. Yeah, that cleans up to 1 over 100. And so there we go. That's good. I'll cross that out. And we have the value, and there's my error is less than that. Cool. I like that. All right, and then number D, an Euler's method question. So bringing back, they didn't ask you to solve the differential equation. Wow, I was totally expecting a separable differential equation solution coming up, but they didn't. Interesting. Neither AB nor BC had to solve the differential equation. All right, I like to do my Euler's method with the table. I'm kind of unique that way. I believe most teachers like to just use the iterative formula. I think better with the table. I do. So my table looks like this. We have a beginning x and y value, and that would be 1 and -1. And I'm trying to get to 1.4 with, usually it's 2 steps. Yep, 2 steps of equal size. So my delta x is going to be 0.2. And so I'm going to go up by 0.2. So 1.2, 1.4. I'm going to make a note to myself that delta x is 0.2. My delta y, I take my differential equation and multiply it by the dx. And so my delta y is going to be 3 minus x times y squared times the delta x. But delta x is 0.2, so I'm going to replace that with 0.2. And then I like to do this last column. It's really not needed, but my new y coordinate will be my previous y coordinate plus my newly computed delta y. And let's get to work. So 3 minus 1 is 2 times -1 squared times 0.2. That's 2 times 0.2 is 0.4. So my new y coordinate is -1 plus 0.4. That's -0.6. And my next delta y is going to be 3 minus 1.2. That's 1.8 times y, which is -0.6 squared, times 0.2. That's kind of ugly, and I'm going to leave it like that. So my new y is -0.6 plus that delta y I just computed, 1.8 times -0.6 squared times 0.2. And then I like to make a conclusive statement that f of 1.4, do I call it f? Yeah, f of 1.4 is approximately -6 plus 1.8 times -0.6 squared times 0.2. Leave my answer like that. I don't know what that is, and I don't care, and I'm not going to try. So there's my answer to number 5. If any mistakes, point them out. Hit that like button because I want you to, and I told you to, right? And I will move on to question number 6.